And we're off. Okay, so this is where we left off, talking about task division, all the different things that happen. Next one, the indexing system. So we'll get a little bit more technical detail about how the indexing system works. So, key things, there's 3 server roles. Number 1, the index servers, which are the set of servers that contain portions of the index itself, basically the list of search terms and all the pages that they point to. The document servers that store actual copies of the web pages. And then spelling servers. Spelling servers are used to process search terms for likely alternate equivalent meanings. So, basic process, user goes to google.com, enters some query, that gets sent to the index. The first thing that happens, looking up the index entries that match that, basically it's going to look for exact or nearly exact matches, semantic equivalent ones, and then the spelling servers are going to check for likely alternate meanings, right? For example, Google might have an actual listing for BGUS, but maybe bugs is a much more common search, okay? Then, index servers are going to retrieve document IDs based on search terms. So whatever documents, whatever web pages match the terms that have been selected through that whole process, Google's going to retrieve the corresponding records and then compare them to each other, right? So the document servers are going to deliver the web pages. When you get the list of search results, you'll have a little blurb. You'll have the title, and you'll have a little slug of text from the page itself. Okay, interesting thing, early paper, I just mentioned this. This is one of the first, if not the first, research paper that they put out. So this is from 1998, I believe. And they talk a little bit about how the system works. Obviously, it's changed a lot over the last 20 years. But the short version is this is how they were, doing the matching back in the day. Okay, so, and the interesting thing here I'd like to point out, these are the search times, right? So we can verify that they do, in fact, do a certain amount of caching. So here for Al Gore, right, the initial query, the total time took 2 seconds. But for the same query, if all of the data is pretty much cached, they can retrieve the results in 0.06 seconds. Even a very, apparently an odd search like search engines, initial total time almost 10 seconds. But again, with the data being cached, if this search turns out to be popular, they can bring it down by almost a factor of 10. Okay, so even from the very earliest time, they were implementing caching to respond to popular searches faster. All right. And there they are. There's the guys. How about that? What? Oh, shit, you can never see the stuff I do. Yeah, all right. I got this thing. There we go. All right, so there's the guys. There they are. And here, this is the list of the chart of times. Okay, so various searches, like I said, search engines about 10 seconds. And if it's cached, then they could do that about 10 times quicker. Okay. Anyway, it's if you're interested, it's an article. IDS majors might be interested in that. Okay. So, index servers, they're grouped into clusters and divided by language. Okay, so within each data center, you have a bunch of different clusters of servers, and it makes sense that if they're, for different languages, they're not going to share the same portions of the index. So for English alone, several 100,000 terms, each of which might be associated with many millions of web pages. Okay, so the index itself, several 100,000 terms, and for each term, you have a very long list of pages, right? Because the page reference is surely several bytes long. So this is many gigs per term potentially, okay, or a gig or so per term. So you're not going to put this whole index segment on just one server. You need a whole room full of servers just to store the index. Okay. So the index gets divided over many servers. Each is going to hold some subset of entries and page references. And queries not in the local language will probably get forwarded to another cluster like we talked about the other day. Okay, although again, if you're in Europe, for example, you have one cluster in, say, you have one data center in, say, Belgium. It's surrounded by several different languages, right? They got French, they got German, they got Dutch, they probably have Flemish, probably some stuff in English. Maybe they're close enough to Italy, they have Italian, right? They have a lot of, in Europe, all the different languages are crowded pretty close together, so could be a little different there. Anyway, So when a search query gets received, the system, number one, performs semantic analysis to identify which index entries correspond to the search terms, right? It's basically going to say, here's the actual search terms, and these search terms are equivalent to these other terms, each of which has their own separate index entry, so we can include all of those. And then it forwards that query to the appropriate servers. It says, okay, index, we got a request for these pages, so let's pull them out and take a look. So, Google doesn't reveal precise system details. However, one thing that you can look up is patent documents where they describe how the process happens. Now, this one I don't recommend reading because it's very long and technical. I'm going to get it here so you guys can actually see what I'm doing. There we go. Ta-da! Query scheduling using hierarchical tiers of index servers. And just to give you an idea of what I'm sparing you, there's a lot of stuff. Okay? But the key thing that we can look for, okay? For example, New York Ethiopian restaurants, right? This is how part of how it figures out which terms are grouped together. Now, if you're a human, you can look at this very quickly and say, oh, New York, that's probably a semantic unit. Ethiopian restaurants, right? That's probably a semantic unit, right? Restaurants that specialize in Ethiopian food. So, what probably makes the most sense is this one, yeah? But Google's going to learn that based on what people actually click on over time. There's no inherent way to learn that otherwise, other than, again, just verifying what people actually click on. So, that's part of the problem. Part of the problem is learning over time which term groupings make sense. The other one, if we fold back a little bit here, fold back way back. They talk about the quick brown fox, okay? So, for example, suppose you're doing a query for the quick brown fox jumped over the lazy dog, if I can find it here. They have New York restaurants again. I'm just going to... Quick brown fox. Okay. I guess that's right. That was the one. Okay. So, again, if you have a page title, the quick brown fox, right, there are all sorts of different ways to combine that. And basically, here's a phrase identification server, scans through these words one at a time, generates what's called a phrase map table. So all sorts of different ways where that phrase could be included in things. So we have quick brown fox jumps over, quick brown fox jumps, the quick brown fox buffer full, da-da-da. All sorts of, and other parts, over the lazy god, which is actually what they have in there. A lot of different possibilities that it might match. Okay, so all of this is basically, this describes the technology that Google uses. A search line of search text comes in. How does Google decompose that line, which might contain multiple semantic units? How does that decompose it and then compare it to actual index entries? Okay, so the short version is, it's a fairly complex process. If you want to read through all this, yeah, you can, but you'll get real bored real fast. This sort of thing is just for patent lawyers. Okay. So, anyway, key thing, query gets decomposed into likely phrases to address the large number of possible combinations, right? If, for example, I enter in a slug of 10 search terms, just the number of terms that can possibly be matches, there's 2 to the 10th. There's 1,000 possible combinations of those that include, at least one of those. Also, when you start allowing the possibility of terms being arranged in different sequence, then that exponentially blows up the number of possibilities. So it's very important that Google does a good job of decomposing the query. Otherwise, the search time is going to be, the retrieval time is going to be exponentially larger. Other thing, the documents are cleverly distributed over servers. Okay, so again, this is kind of technical. You don't need to know it in great detail. But here's the thing. Number one, server cluster is divided into segments so that each phrase entry is confined to one segment, right? So you have this whole cluster of servers for like the English language index, say, and there are different segments in there where for any particular search term, a phrase entry is only going to be found in one segment. And remember we talked the other day about you want to do this balancing between having a lot of servers to allow for parallel operation, but you don't want to necessarily involve every server in every operation. So the segmenting is basically the sizing there is designed to strike the right balance between those two things. The other, there's a mathematical function. It's a complex thing. You won't learn about this unless you're a math major. Mathematical function used to divide the entry list and assign documents to servers independently of the phrase. So basically that means for any particular term, it's going to be located on a particular server, and there's always going to be an easy way to find it. That's the point of this mathematical function. It makes it very easy to locate a particular page. Okay, so if you didn't have those two things in place, basically every index server would be involved in processing every request, which would slow down the system a lot. Okay, the other thing, Google does optimize the analysis sequence. For example, if you start out with a very large set of possibilities and you want to analyze all those first, that's going to necessarily involve a lot of servers. So if you can reduce the number of possibilities, for example, you get a long query string and you want to quickly decompose that into the most likely combinations that mean something, you do that first so you don't have to pull out a really huge number of web pages. Okay. So, little picture here of the indexing system design. And again, this is technical. Don't need to memorize this for the exam. I'm just giving you some insight into how Google does it. So, for any particular cluster, number one, the index gets divided into n sections and assigned to server tiers to segments within that cluster. Okay? Each index entry, right, so for a particular search term in the list of the associated pages, that can be broken up into one or more shards. Shard is basically a fragment. Okay, so it gets put into different pieces on different servers, and that allows doing parallel operation. Then there's an assignment function. This is that mathematical function we talked about. It ensures that a given page is going to be stored in the same shard for any entry, including the page. What that essentially means is even though I might have a set of search terms that in multiple ways access the same page, that page is going to be located at the same point. I only need to store one copy of that page, and then the search term will always have a clear link to it. Okay? Again, this is a little bit technical. I get that. So what are the key takeaways? I will mention what the key takeaways are. Number one, the index is very large. Not feasible to store index and pages on one machine, right? You need a whole warehouse full of servers, okay? Number two, each page is ideally only stored once, regardless of how many index entries reference it. Okay? Otherwise, you'd need thousands of copies, right? One per unique search term. That would be crazy, right? Okay. So that's it. What else? Number three, different data centers hold different portions of the index, which may overlap, okay? Which means they may have pages or index entries in common, okay? For example, both a Chicago and LA data center might have the same articles about breaking U.S. news. Okay? Those are the key takeaways. If you understand all that, that's enough to go on for IDS 200. Okay? But this other stuff I'm putting in there just so you recognize it's a whole pretty complicated process. All right. So, the rest of it, document servers. So, Google stores tens of trillions of page documents and, of course, multiple copies of each. Some of those are for backups. Some of those are for basically allowing parallel operation. Like if a particular search is very popular, Google might store different copies of more than the basic 3 copies for a while. Now, as we've talked about before, document objects like web pages, they don't have a definite structure. So they get stored in a separate system. It doesn't make sense to store them on an ordinary relational database because they don't have a fixed structure that you can fit it to. Also, because the system is very, very large, right? Think about tens of trillions of page documents, very large system. It runs on a whole separate set of hardware. It's its own separate system. So, when a query gets processed by the indexing system, it's going to retrieve the matching document. So essentially, Google's going to analyze the relevant variables in each document. It doesn't want to look at the whole web page. It just wants to look at some distilled version, right? Like what's in the title, what's in the headers, what's in the first paragraph maybe, what are some metadata about the images. It doesn't need to scan the entire page from scratch every time. Okay, so, and when the results get returned, right, users get a blurb of text, typically a title and a first few lines of text. So, that's the basic process. And then there's layered rounds of page ranking within Google, how Google figures out which of the matching pages it returns. Well, before the documents get retrieved, the first thing is the search term match strength, right? So Google will say, are these terms present? Are they co-located? Right? Does this page match the semantic unit for multiple terms, or does it contain the words separately in case it's a weaker match? Then afterward, once Google has retrieved the set of pages, then Google's going to compare all of those against each other by analyzing the document itself. Okay. So, as far as anybody on the outside knows, Google uses a common methodology for page analysis. Basically, uses the same ranking model, same page analysis model for all the pages, regardless of what the content is, what language they're in, whatever. Works the same way for all of them. And what it does fundamentally, it reduces all that page content to a limited finite set of variables. So, title and some blurb of text, and then the hundreds of other factors like page objects, things like that. And because this part of variables is a uniform structure, right? Not like the page itself, but it pulls that same kind of content from every page. Because that has a uniform structure, it's more or less compatible with relational database models. So, this is what Google uses, right? A distilled version of the web page. It's what it uses to do the ranking analysis because it's much faster to do it that way. However, Google does store the documents in their original form. One reason, this allows performance analysis and revision of search algorithms. If you didn't have the pages in their original form, you'd have to go get them all before you thought about, say, extracting some new data from the pages or looking at it in new ways you hadn't before. For this, the original web page documents, again, no inherent structures for something like NoSQL is a sensible option. And Google also has what's called Bigtable. Bigtable is for this distilled version. So I'll show you in a second. Okay, so for document storage, this Bigtable database has a few key features. Number one, so it's essentially an extended relational database. In a lot of ways, it works like a relational database, but there's a few extra features in there to make it better for working with web pages. Number one, it's automatically sorted so that related rows are stored next to each other, so you don't have to sort through the whole database. Right? So imagine, here's your giant table. With, say, 10 billion pages. Ideally, you don't have to comb through that entire thing for a search, right? So suppose our topic is sports. And within sports, there are many subtopics, but suppose one of the topics within there is Chicago Cubs. So we would identify that as being, one of the significant subgroupings and store all of those Chicago Cubs related pages together. Okay? And that way, if a search came up for Chicago Cubs sports, then you know what? We wouldn't have to search this entire table. We could just very quickly go, oh, all the pages I might want, they're all right here. This is what I need. Okay, so it allows retrieving data much faster in that sense. Another thing, column families. So, regular relational database, okay, we'll have something like this. So, we'll do a table with columns. If I wanted to do, so regular relational database, if I had a set of records, suppose these are all the things about Chicago Cubs, right? I would need one thing for the title, one thing for header 1, one thing for header 2, header 3, some text, image 1, image 2, image 3, ... For everything that might have multiples, I would need a separate column, right? And of course, there's no real upper bound to the number of images a web page might have. Could have hundreds. Well, if I'm just doing this with a regular relational database, I have to hold room for 100 images, right? And if there's a lot of headers, I have to hold room for all those different headers. Anything that there could be more than one of on a web page, if I'm doing this in a standard relational database model, I have to have that column already available for the maximum number of things of that type that might occur, which is going to be very large, right? You don't really want to do that. So what Bigtable does instead, it has groupings. So for title, sure, there's only going to be one title, but then I could have a group of headers, right? And this, when necessary, it could point to other tables or other records within the table, say, oh, here are these things. It can have more than one. Likewise, for images, I have a record of whether there are images or not. If there are images, it's going to point somewhere else to that group of images. This gets around the way, so Bigtable appears like a relational database, but doesn't act like one. Okay, I don't need to have specific columns for every possible unique thing. I can say, all right, there's going to be a group of headers. There's going to be a group of images, and I can point to some other location, possibly on that device, possibly elsewhere, where all those things are. Okay? Most likely on the same device for speed, though. The other, sparsely populated. Again, Google has a super complicated algorithm that considers hundreds, literally hundreds of web page factors. So Google has a very complicated algorithm for ranking that considers hundreds of factors. Many pages may lack many or most of these factors. So, Google doesn't want to store exabytes of non-data, right? It doesn't want, at Google's scale, when they have tens of trillions of these pages, it doesn't want to store all that as just zeros, right? For all those different factors, no, it doesn't want to do that. So instead, Bigtable can let groups of fields be zeros and save space, right? Basically, if there's a set of fields that are all zeros, Bigtable is going to say, you know what, nothing here. The next field I have is like 10 or 20 or 40 fields later, okay? You don't have to separately store zeros in all of them. You can group together the empty fields as well, okay? All right, so that's the gist of Bigtable there. The short version, it sort of acts like a relational database model. It's pretty fast like a relational database model because all of the same factors that you're considering in web pages, that can be pretty well standardized, but it allows for the fact as well that different web pages do not have the same format necessarily. Can I go where? Picture? Okay. Okay. So that's it for indexing. Okay, and again, the key takeaway, number one, yeah, Google stores documents in their original form, but when it's doing the comparisons for ranking, of course it's going to use the distilled version of the page because it doesn't want to consider absolutely every aspect of the page and hunt around for whether those things are there or not. It has all of that information pre-distilled and available to use. Okay. The other thing, spelling servers. So, spelling servers are designed to detect spelling errors, as you might guess. So what they do, they receive the original search queries, they identify misspellings by comparing query ranks, and then they return a list of likely options. So fundamentally, the idea, how does Google recognize that a word has been misspelled? Well, the biggest evidence is that it's a word that, or a phrase that Google hasn't seen before, but it's very similar to a fairly popular phrase, right? That's the best signal there. Similar technology was used in what was called the Google Search Appliance. I don't know if anybody's ever seen them, but last I checked, there was this Wikipedia article. There we go. That yellow thing there basically looks like a server. They've been around for a while, but it's phasing out. Phased out of the appliance in early 2016. If you have one, you can still use it, but Google wants to get people doing document storage on the cloud, not storing them on their own premises. Anyway, so you can still have them, they're just not really supported anymore. Anyway, the nice thing about these search appliances, basically they did document indexing for 10 million or more documents, and they did spell checking during the index review. So one of the problems, if you think about it, if you're an organization and you have literally millions of documents, it's almost mathematically certain that some of them are going to have spelling errors. And it would really suck if this document got lost in this crowd of millions of other documents and became, for all practical purposes, unfindable because there was a spelling error in it, right? You're looking for something with the CEO's name, but for whatever reason, that particular document slightly misspelled the CEO's name, and so you didn't find it. Yeah? I don't know if you guys remember the thing about, there was the whole thing about Hillary Clinton's emails, and most of them were destroyed. But the ones that they found, right, because there were different waves, right, where they'd find like a few and say, oh, look at these. A lot of the ones that they found were actually ones that had spelling errors in them. So they hadn't, the people who were doing the searching to destroy them, they basically looked through, oh, let's find all the terms that match. If we find them, we got rid of them. But somebody had like a letter out of place. They didn't find that one in the search, and so it stayed on the device. Anyway, so spell checking is basically very important for document storage, whether it's stuff that you want to keep, stuff that you want to destroy. Imagine if you're a business and you have some sensitive documents, you want to make sure that you get rid of all the correct ones. Well, again, spell checking is absolutely important. All right. So, spelling correction. For over 10 years now, Google has corrected user spelling. Sometimes actual deliberate definite errors, right? For example, if you find a search term with no index entry or very few matches, but sometimes it's a correct but unusual word that's very similar to popular search terms, right? Sometimes you can have, like for example, if somebody comes up with a new video game that is a conventional word, but they replace a C with a K, for example, to make it look cooler, then, it wouldn't ordinarily show up right away. So, how does spell correction work? Well, number one, query rank. The query rank is better if it's a popular query and if it's rarely revised. One of the ways Google recognizes that a word has been spelled wrong is if somebody types it in, goes to the search results, and the search results are all screwy because they spelled something wrong, and then the person goes back and does the search query with the word spelled correctly. Okay, then Google says, oh, you did a revision there. Now, correction candidates typically have a low query rank, right? They're not very common. When they do appear, they're often revised, and they're similar to a highly ranked query. Okay, so again, you have an oddball term that's close to a common term. Yeah, Google's going to guess that that's a spelling error. And this similarity can be individual words, can be semantic units, could be observed from sequential searches. So we did some of this, right, with bugs versus BGUS, but with semantic units too, right? If we did software BGUS, then we got software bugs as the likely candidate. One of the fun things you can do with Google, and I say fun, it's not all that fun, but one of the things you can do is see just how crazy misspelled words can be, and you still get actual search results. So let's say, and a lot of times if you have like the first 4 letters or so, it'll probably catch it. So I could do Uniblurgers of Illinois at she fuck you. Oh, I didn't get it. All right, let's go back. Too much. Close. Now I'm getting better. I got university birds. I thought blurs was birds. Okay. Universe. Let's get rid of that B. B is confusing. Let's do univlurs. Yeah, I know. I'm just seeing how. Oh, University of Illinois at Shifu. Oh, here we go. But see, we're getting some of the stuff. Must include Shifu. All right. Yeah. So you can do stuff that's pretty messed up, and it'll do the best it can. It's kind of fun. All right. Okay. So, Last thing, indexing troubles. Google's index is very large, but you may notice you go to Google all the time and you never get the message, sorry, this part of the index is shut down. Please come back in, an hour later, right? You never get that message. So how does Google handle updates in real time? Well, number one, as far as Google users are concerned, the pages, the search results are read-only. So that means Google can be changing one copy of it and still let you look at it. Okay, they can have concurrent access in that sense. The Google system can be changing stuff within a table and still provide you with read-only results from that table. Second, the system is designed to allow small-scale isolated updates very quickly. So one of the things about Bigtable, remember I said groups of related records are stored together? So if some news comes up about the Chicago Cubs, every now and then Google will do a batch where they'll say, oh, we have a few articles changed about the Chicago Cubs, let's update the index, right? And all those pages are close together in storage, so it can be processed very quickly. Last, duplicate copies are generally maintained locally, right? So even if somebody comes in, does a search on something, and the index is being updated, they can access the other copy. Excuse me. Okay. The other thing, eventual consistency, right? So just like Facebook generally has a philosophy of eventual consistency for things like who's liked your photo, stuff like that. So if Google is doing updates, different users might receive slightly different results for the same query, right? So if there's an update process going on one copy, somebody starts, the update process, they get a cached version, another person gets the query results with some of the updates in, another person gets the query results immediately after with all the results in. So while updates are going on, yeah, different users might receive slightly different results. However, it's a read-only system. It's not a transaction system where you got to make sure that the money is handled correctly. We also expect some imperfection, right? Nobody expects Google to deliver absolutely perfect search results every time, to read your mind and know exactly what you're looking for and put that at the top, right? Google's going to give you a set of candidates, and hopefully they're pretty good, and people understand that, yeah, they're not going to be perfect. Last, if you did keep the database perfectly consistent, it's going to slow down search results too much, especially at Google scale, right? Basically, if you're changing anything within a table and you say, well, I'm going to lock this table while the search is going on, but think about it. Google has, these index entries that are potentially billions long. Anytime one of those is getting updated, if you're doing the whole thing, it's going to take a while. And if you lock that, yeah, you're going to have to keep a whole nother copy of it around, or people are going to have to wait. So it's not a happy trade-off either way. Definitely if you say nobody can look at these results until all the updates for those results are done, and you're talking billions of updates, it's going to take a while and the search is going to be stopped for a little while. So they don't want to do that. They can live with some imperfection. Okay? All right. Questions on any of this stuff? All right.